It's Mr. Tro here. We are going to start talking about a couple different types of reactions in terms of classification. They're called endothermic and exothermic reactions. Now, you may remember from biology class the terms endo and exo. You might have heard them with skeletons, endoskeleton, exoskeleton, things like that. So generally speaking, endo means inside, and exo means outside or in or out. And we can kind of use that when we apply it to this thing called exothermic or endothermic. When you hear the term thermic, you kind of think temperature, like thermometer, heat, what have you. So in chemical reactions, in many of them, you're going to get heat changes. You're going to get a reaction that either creates heat that goes out to the surroundings, makes the outside surroundings hotter, or you're going to have a reaction that takes energy or heat in and leaves the surroundings feeling colder. Now, it's not true in every reaction, but generally speaking, that happens in many reactions, okay? So to start, we're going to talk about a couple terms here. When you have a chemical reaction, the reason a reaction happens is it's driven by this thing called chemical energy, okay? And simply put, chemical energy is just the energy that is stored within bonds. Okay? It's the energy that's stored within bonds. Okay? A couple things. In a chemical reaction, two things are going to happen with bonds. Bonds are the electrostatic attraction or the attraction between atoms. And in order for a reaction to happen, bonds have to break in the reactants and new bonds have to form in the products. So the concept or the idea of breaking bonds that typically happens in the reactants, breaking bonds typically takes energy. So breaking bonds requires energy. So that's the in part. That's where energy will go in to a chemical reaction. Forming new bonds, and this happens in the products, forming bonds releases energy. And that's the out part. So you can kind of see how endo and exo would refer to those processes. Okay? And we'll talk more about that in a few minutes. Activation energy. If you activate something, you turn it on. If you get a new cell phone, you need to activate it. It's the process of making the account active or turning it on or getting it going. So activation energy is simply the energy that is initially required to get a reaction going. Sometimes you can put chemicals together and they look at each other and they go, you know what, we want a bond. I want to break these bonds. I want to form new bonds. I'd like to get this to happen, but we just don't have enough energy for that to happen. So you can usually get that to happen by, maybe like a spark. So like in a car engine, a spark would be enough energy for that gasoline, the octane, to ignite. Maybe it's a flame. Maybe it's just adding heat. There are lots of different ways you can add energy to a reaction, but sometimes they need that to happen. Okay? All right. These graphics down here are just showing the fact that if you want to break a bond, energy must be supplied to break chemical bonds. So if we want to break this bond, it takes energy. Okay, if you want to break a bond. So it takes energy. Energy is added to break bonds. Okay? And now these are separate. So now those atoms are separate and they are free to go and react and bond with something else. So if you have two separate atoms now and they're going to form a bond, like down here, so a new bond is formed, when that happens and these two atoms come together and they form a bond, whether that bond is ionic or covalent, we're going to talk about that later, that process has energy being released. So new bond formed, energy is released. Now, typically the energy is released as heat, and so we would feel that as the surroundings getting hotter. But as we're going to learn here, breaking bonds takes a certain amount of energy, and forming bonds gives off a certain amount of energy. It's kind of like a bank account where you're going to have a negative part to the process. You're going to have to spend money, okay, to break the bonds. You're also going to have a positive part where money's coming in or what have you, and energy is released. So there's always this balance between how much energy does it take to break the bonds and how much energy does it take, or how much energy is given off when bonds are formed. Okay, so let's say this took 100, and there's a term for you, joules. I remember that from first semester. That took 100 joules to break the bonds, and this process gives off 150 joules. Well, if that's the case, then yeah, there's going to be more energy given off on the latter half of that reaction, making the products. And so, yes, that reaction is going to feel hot. But on the flip side, if it took 100 joules to break the bonds and you only get 50 joules out when new bonds are formed, then you had to put energy into the reaction, and that's going to leave the surroundings feeling colder. Okay? We'll get into that a little bit later. So, in an exothermic reaction, more energy is released than is added into it. Okay, so another way you can say that is with an exothermic reaction. You can say more energy released when bonds form in the products than is required to break the bonds in the reactants. Okay. And before we move on to endothermic, I just want to scan down. If you notice, in an exothermic reaction, which is the right-hand side of this column, this chart, you can see that the reactants have a certain amount of energy, and the products have a certain amount of energy. And so now, overall, from where you start to where you finish, you end up below in terms of energy. The products have less energy stored in their bonds, which means that energy is released to the surroundings. Okay. So graphically, that's showing that the energy released is greater than the energy that you have to put in. You only have to put a little bit of energy in to get the reaction going, but a lot of energy is released, okay? An endothermic reaction is if more energy is supplied than is released. Let's do this in a different color. So if more energy is supplied than is released in a reaction, then you have an endothermic reaction. So in an endothermic reaction, it takes more energy to break the bonds in the reactants than is released when new bonds form. Okay? In the products. So that's the general sense. It's kind of hard sometimes for students to grasp this big picture. It's why we look at the diagrams down here. And if you see in the diagram, the reactants don't start with a whole lot of energy in their bonds. They're at very low chemical potential energy. And then we keep adding energy to those reactants. And eventually, if we add enough energy, we can break the bonds. And then they form products, but those products are at higher energy. So it's kind of like saving money, putting money into an account. We're not releasing the money, we're not spending it. We end up having a gain in energy into the products. Okay? So we say energy is absorbed. Okay? And it's absorbed from the surroundings. So now if you think about this, if you have an exothermic reaction where the extra energy is released to the surroundings, you can think of that energy as heat. And that would make the surroundings around the reaction hotter. Maybe the beaker gets hotter. The air around the beaker gets hotter. If you're doing an endothermic reaction, it's going to draw energy in from the surroundings, and it's going to leave the immediate surroundings feeling a little bit colder. So that's a telltale sign between the two. Okay? All right. So we obviously, these definitions right here could be translated right down there. I'm just going to write a very simple version, okay? So an endothermic reaction means the energy in is greater than the energy here. The energy in to a reaction is greater than the energy out. We say absorbed and released, but it might be easier just to memorize it as the energy that goes into a reaction is greater than the energy that's given out. Okay? What that means is that the reaction overall, it absorbs energy. Okay? And you can see that energy goes in as you go up that graph. Okay? How does it make the surroundings feel? Remember, the surroundings is not the reaction. The surroundings is the area around the reaction. So that would be the air or maybe the liquid that the reaction's happening in, the beaker, okay, the tabletop, things like that. Do the surroundings feel hot or cold? Well, if the energy is drawn in from the surroundings, it's going to leave the surroundings feeling colder. They will be colder than when you started. Okay? Looking at the graph, in terms of energy, this y-axis shows chemical energy. It shows the amount of energy that's in the bonds in the reactants and products. Yeah, it's pretty obvious that the products have more energy, because we are literally piping energy into it. We're pumping energy into this reaction. Okay? Real life examples. Off the top of my head, I would say photosynthesis does this. Right? You have things like carbon dioxide and water and a bunch of energy. So that would be the sunlight, right? And what that's going to make is it's going to make glucose. It's going to make sugar. And then that plant uses that glucose for lots of different processes, right? What I want you to do is do a quick search, and I want you to find another example of endothermic. There's lots of them. So on your own, find one. Okay? All right, let's do the same thing for the exothermic. Now, what you're going to notice is that they're pretty much going to be opposites of each other. Where endothermics, the reactants start at low energy and the products end up at high energy in terms of bonds. The reactants in an exothermic reaction, they got a ton of stored energy in their bonds, which is useful for us because we can break those bonds and then form products that are at lower energy. We can release that energy to the surroundings, which is quite useful. Okay? It's really useful in something like gasoline, which is octane. So we could have gasoline burning. That would be a great example. We learned earlier, this is combustion, right? You take a fuel, you react it with oxygen, you give it a little spark. In this case, right, it needs a little bit of energy to get over that hump to start those bonds from breaking. And then once that happens, the reaction starts and the reaction gives off a ton of energy, and now the energy is there. It's already there for the rest of that octane to react. But you have that reacting into carbon dioxide and water, and that's combustion. Now, we need to balance this, but we're not going to balance. It's just an example, right? We're not going to balance it out. Okay? And again, tons of examples of exothermic reactions. Why don't you find one as well? Okay. Before you do that, looking at this chart, because the reactants have high energy and the products have low energy, we can say that which has more energy, the reactant or the product? We would say, yeah, the reactants have more energy. Okay. And since the products are at lower energy, that energy had to go somewhere. And that energy goes to the surroundings. And if it goes to the surroundings, then it makes the surroundings feel hotter. Now, if you notice this graph on the left, energy is constantly going into the reaction. That's why it's an upward slope. So that's why we said it absorbs energy. In this reaction on the right, once it gets started, energy is constantly leaving the reaction. Okay, so it is released. So with that being said then, we can say that the energy in is less than the energy out. Okay? So I hope that makes sense to you. That's the lesson, the second lesson here in this part of the unit. All right, hope you have a good day. Bye-bye.